Okay, so good morning and let us get started. We stopped at this point in the last class where we were discussing about the different laboratory methods for estimating the hydraulic conductivity. And we spoke about these two methods, the constant head permeability test and the falling head permeability test. And so I think I asked a question about which of these is suited for fine grained soils and which of these is better suited for coarse grained soils. Okay, so as it turns out, I think I misspoke last time. So the constant head permeability test is better suited for coarse grained soils, and the falling head permeability test is better suited for fine grained soils. Now, I do not suggest memorizing which is better for which and so on. I prefer coming up with a logical understanding of why uh, it is not a good idea to do a falling head permeability test for a coarse grained soil. Now, what is the principle of the falling head permeability test? I have a sample, and then I have water in a long tube with some graduations, and then what I do is I measure the time it takes for the water level to go from a particular level in that tube to another level. So which means the water level in that tube is falling. That's why we call it the falling head permeability test. Now, if I have a coarse grained soil in a falling head permeability test, okay, and let us say I want to measure the time it takes for the water to drop from a height of, let's say, 20 centimeters on that tube to 15 centimeters, 5 centimeter drop. Okay, I want to measure the time it takes to drop by 5 centimeters. If my soil is coarse grained, then I will have a very high hydraulic conductivity, which means it will take a very short duration of time for the water level to drop from whatever 20 to 15 or 15 to 10, any two uh, any two different heights. Okay, now as soon as the time it takes for the water to drop reduces, right? Remember, when you're doing a laboratory test, you have to start the stopwatch when it is at 20, and then again stop it when it hits 15. Okay, and remember, there's a reaction time each time you do it. So the first time you hit start, there's a reaction time of maybe 0.3 seconds or 0.5 seconds, right? Varies from person to person. And then again, on the reaction time when you click on stop. So which means potentially your uh, your time can be off by 1 second. And suppose it only takes 5 seconds for the water to drop from 20 to 15 centimeters. It in reality it takes only 5 seconds, and your reaction time itself is 1 second. So that's a 20% error that you're adding uh, to your measurement. Okay, so your estimate of hydraulic conductivity is going to get impacted by the way you measure it, right? So that's why you don't do the falling head permeability test for a coarse grained soil. What you do is you do it for a fine grained soil where it may take 5 or 6 minutes to drop from 20 centimeters to 15 centimeters. So even if over a duration of 5 or 6 minutes, your reaction time of 0.5 seconds or 1 second doesn't play a big role. Okay, so that should be the way to remember it. Don't try to say C for constant head, C for coarse grained, okay, matching, F for falling head, F for fine grained. You know, it's funny what happens when you get to the exam, when you're sitting there and thinking about, I mean, of course, this is a minor question. I'm just giving you an example. You think you memorized it, you come there, you remember the exact opposite. A C is not for course, it's for fine, and F is for course. Something like that will happen, and then you kind of mess it up. It's better if you understand it conceptually, right? It takes more time for the water to fall over a certain height, and that is better if the permeability or the hydraulic conductivity of the soil sample is lower, which is what happens for a fine grained soil. And therefore the falling head permeability test, where the time it takes for the head to fall by a certain predetermined height is measured. So that is the way to remember it. Of course, in the constant head permeability test, you're not measuring the time at all, so therefore there is no problem with that measurement. Okay, any questions? I'm not giving you the equations for the constant head permeability test and the falling head permeability test. Those are available online in any standard textbook. Also, you can find them. And it's not very hard to figure out. Okay, so I'll leave that as an exercise for you. Okay. All right, let's move on. Now, we spoke about Darcy's law. Now, we'll spend a little bit of time trying to understand what are the range of values, or how valid is this Darcy's law, and what are the range of values for which it holds good. Now, you might remember that we used to have this idea of the Reynolds number. Re, which we define as rho v d by mu. We used to use this very often for pipe flows, right? And turns out that we can use the similar Reynolds number for flow through porous media as well, flow through groundwater soil samples as well, and use this to find out for what range of these Reynolds numbers is Darcy's law valid. Okay, but in the case of groundwater, this Reynolds number will be defined slightly differently. Instead of rho Vd, I'm going to call it rho Q, small q being Darcy velocity, right? And then instead of the diameter of the pipe D, which we used in pipe flow, we'll use some representative grain diameter. Okay, so you may use D10 or D30, whatever it is, divided by mu. Okay, so this is the definition for Reynolds number for groundwater flow. Okay, and then what it now about this, about the numbers that I'm going to write, there is some controversy on what exactly the values of Reynolds number are for which Darcy's law is valid, but I tend to agree with this. Okay, so as long as Reynolds number is between 1 to 10, okay, it's in the range. Okay, I mean, if you want to be very precise, I can put 1 less than or equal to Re less than or equal to 10. As long as Reynolds number is between 1 and 10, Darcy's law is assumed to be valid. Darcy's law is valid, right? Beyond the Reynolds number of 10, what happens is that the flow tends to become more and more turbulent, and therefore Darcy's law is no longer valid, right? Now, this notion of laminar flow and turbulent flow is very easily understood, right? Flow is very smooth and predictable when it is laminar, and it's very random and unpredictable when it is turbulent. So as long as the Reynolds number is between 1 and 10, some people say less than 10, they don't even give this lower limit of 1. Okay, but I tend to believe that this 1 to 10 range is a good way to understand this validity of Darcy's law. Now, what happens is, when Reynolds number becomes less than 1, which means it goes outside this range, when the Reynolds number becomes very small, what happens in that case is that the viscous forces tend to dominate so much, right, that the flow itself almost ceases to exist. Okay, when Reynolds number is very low, it typically happens, when I say very low, I mean less than 1. Okay, as long as it is greater than 1 and less than 10, Darcy's law is valid. If it's greater than 10, it's not valid, or it becomes less valid. Let me put it that way. And if Reynolds number is less than 1, there too, basically you're in a situation where the soil is very highly fine grained. Okay, very, very fine soils, which means the Darcy velocity is very, very low. And when that happens, you may end up in a situation where the flow is basically the flow itself is not happening. Flow itself is almost stationary, right? And so therefore, in that kind of a situation, we tend to say that, the viscous forces are too high, right? And therefore almost no flow is happening at all, and therefore we tend to remove that portion of the Reynolds number from the validity of Darcy's law. So, but fortunately for us, in a wide variety of situations, Reynolds number falls between 1 and 10, and so therefore we can happily use Darcy's law for all practical purposes. in 99% of situations where you're dealing with groundwater flow in the real world, the Reynolds number is between 1 and 10, and therefore there's no need to worry about it. But for theoretical purposes, it's important for us to understand that there is a limit to somebody's joined. Okay, my suggestion to all of you is to please join the Google Classroom using using your using your IIT Tirupati ID. Then when you join the call, you don't have to be admitted into. There are a few people who have not yet joined the classroom, and therefore every time you join the call, I have to physically admit you into the meeting. That's okay. It's not a big deal, but I think it's better if you can join the classroom in any case, because whatever updates I'm posting are there in the classroom, and then I expect that you should all be watching out for the updates that come on the classroom. Okay, so much for the validity of Darcy's law. It's valid between Reynolds number of 1 and 10. Okay, let's move on. Any questions before I move on? Any questions at all? Please unmute yourself if you have a question, because I'm not able to see if you raise your hand. Sorry about that. Okay, let's move on. Okay, so now we are going to spend a little bit of time talking about the various geological formations where groundwater generally occurs. Now, you might be familiar with some of these terms, but I'm just going to um, quickly define some of these. So the very first geological formation where groundwater occurs is called an aquifer, right? So an aquifer is one which both stores and transmits water in substantial quantities. So any geological unit that both stores and transmits. Transmits means it allows water to move, right? It both has the capacity to store water and to allow that water to move in substantial quantities is called an aquifer, a geological formation which allows both these processes, storing and transmission of water, is called an aquifer. Okay. Now, the next type is called an aquitard. Okay, an aquitard. Now here it allows storage, but relatively small capacity for transmission. Okay, before I forget. So for the aquifer, the general example for an aquifer is sand, gravel. Those kinds of materials are considered to be aquifer material. Okay. Then aquitard, as I was saying, is similar to the aquifer. The difference is that it allows storage of water, but does not allow, but has very relatively small capacity for transmission of water. Okay, so does not allow transmission very easily. Okay, so this would be something like sandy clay, silty clay, and so on, or silty sand, something like that. Okay, so these kinds of materials can be thought of as an aquitard, right? So it comes from the you take a portion of the word retard. Retard means not allow transmission. Okay, stops transmission, something like that. Okay, then the third variety is called an aquiclude. Okay, now here now it's just how do I say this? It's just some of these things are not these classifications that I'm giving you is not a very watertight compartment, that this is aquifer, this is aquitard, this is aquiclude. These distinctions are matter of degree. Okay, they are not very precise distinctions, and you can't say that this is an aquitard, this is an aquifer. Everything depends on the context. Okay, an aquiclude is something that allows storage, but the transmission tends to zero. Okay, tends to zero. Now again, you'll say, what is the difference between relatively small and tending to zero? Okay, tending to zero means it's almost almost insignificant. Relatively small means some amount of transmission is still possible, something like that. Okay, so don't think of these as watertight compartments. This is a kind of a uh, uh, not a very precise distinction. Okay, so for aquiclude, a good example would be clay, CLAY, clay. Aquiclude is AQUICLUDE. Okay, then the last one is aquifuge, AQUIFUGE. Now in this, both S and T tend to zero. And for this, the classic example would be hard rock. If I have a very, very hard rock, it can neither store water nor transmit water. Of course, if it cannot store water, there's no question of transmitting, right? So these are the different kinds of geological formations and the context of how they behave in the context of groundwater. Okay, so you have the aquifer, which allows both the storing and transmission of water in substantial quantities. Aquitard, which allows storage but relatively small. Now this relatively is relative to aquifer. Okay, it has a relatively small capacity for transmission of water. Aquiclude is something which allows storage again, but transmission is not relatively small, it is close to zero, right? Almost zero. Okay, and then you have the final category, which is the aquifuge, which is something which neither allows storage of water nor allows transmission of water. Both these capacities tend to zero, right? And you have these different examples for these different and as I said, these distinctions are not to be taken very, very seriously. So for example, if you are in a place like Karnataka or Andhra Pradesh, where you have hard rock aquifers. Okay, see now you see the distinction in the the kind of contradiction in the terminology itself. I'm calling it a hard rock aquifer. Okay, because the hard rock has some fractures, and so the water is actually stored in those fractures, not in the rock. Okay, so in such a place where you have very less water available, even sandy clay will be called an aquifer. Although in this classification, I have listed sandy clay as an aquitard. If I have a hard rock aquifer, even sandy clay will look like an aquifer. Okay, but if you go to maybe Uttar Pradesh or Bihar or anywhere in the Indo-Gangetic plain, which has nice sand and gravel aquifer, there even a little bit of clay, and then you will say, hey, this is an aquitard or whatever, aquiclude or something like that. So these distinctions between these different types of geological formations, or how you classify them, totally depend on the context, the local context. If you're in a place where there's a lot of water available, even if I have a slightly lower transmission capacity, then you will think of it as an aquitard. But if I'm in a place where basically there's hard rock aquifer, even clay will look a little bit will look not so bad. Okay, because it's all with respect to the context of that particular location. Okay, so just keep that in mind. Now, although I've given you all these different terminologies, most of the time we will only work with aquifer and maybe a little bit of time with aquitard. There's aquiclude, aquifuge, and all that. We don't really get into that. Rest of the semester, we will only talk about aquifer and a little bit about aquitard. We will not spend a lot of time talking about aquiclude and aquifuge. So it's a textbook kind of knowledge, but it's important to have this kind of knowledge, especially if you're taking a a postgraduate level course in groundwater, you should have some fundamental idea of these terminologies. Okay. All right. So now we are going to spend some time looking at aquifers. Now, when it comes to these aquifers, there are some four. I mean, I've just listed four. There might be a few more minor varieties, but these are the broad categories of the different types of aquifers that are present. The first one is the unconfined aquifer. I'll explain what all of these different terms are with a schematic diagram. But for now, let's just go through these terminologies first, right? So first we have the unconfined aquifer, then I have the confined aquifer, then there is a thing called the perched aquifer, and then there is the leaky confined aquifer. Okay, so I will try to draw all of these or depict all of these with a schematic diagram. Okay, what is this ASA? Sorry, that shouldn't be there. Just give me a second. Okay, is my screen visible again now? Yes, screen visible.
Yes, sir.
Thank you. Okay, so let me just draw a conceptual picture of this. So I have the land surface. Okay, okay. So let me just change the color here a little bit. Hmm, okay, so let's just go back to this. Okay, so here I have these different layers that I've drawn. This is a cross-section view of a the different aquifer units below the land surface at a particular location. Okay, so let's just imagine this. So this is my land surface right at the top. So this is land surface. This blue line that I've drawn is the water table. Okay, so this first aquifer that is present here is called the unconfined aquifer. UNCONFINED. Okay, so the reason it's called unconfined is because the water table is at atmospheric pressure and it is free to move up and down. Okay, there's no constraint. It can go high and can even touch the land surface. It can go down and so on. Okay, so this unconfined aquifer is called unconfined because the water table is at atmospheric pressure. Very important distinction. Okay, now below this unconfined aquifer, let's say I have some kind of an aquitard. Okay, some kind of a low hydraulic conductivity unit. Okay, so this unconfined aquifer may have a hydraulic conductivity of, let's say, 5 meters per day or 10 meters per day, something like that. And then I have an aquitard which has got a hydraulic conductivity of maybe 0.1 meters per day or 0.01 meters per day, comparatively like 10 times lower than, or 10, what is it, 100 times lower than the unconfined aquifer. Okay, and then here below that, the next aquifer that I have, this one is called the confined aquifer. Now, a confined aquifer typically must have, a confining unit both above and below it. So in this case, I have this aquitard above it. There's one more aquitard maybe below it. Okay, so there's an aquitard above and an aquitard below. And this aquifer unit that is present between these two, between these two aquitards, we refer to it as a confined aquifer. Why is it confined? Because there is, some unit that is present above it and another unit that's present below it, which keeps the water inside this geologic unit under some kind of pressure. Okay, so the water in the confined aquifer is typically at pressure, right? So when you drill a well, the water will rise up until it equalizes with the atmospheric pressure, right? So that's what I refer to as a confined aquifer, because it does not allow water to come into it either from above. So this is not allowed. Okay, so no water can enter the aquifer from above or below. Okay, then it's a perfectly confined aquifer. Okay, please understand this. If no water is allowed to enter the confined aquifer from above or from below, from other aquifers, then this would be a perfectly confined aquifer. Remember in the previous slide, I showed two types of confined aquifer. One is this confined aquifer right at the top. I'm not adding the word perfectly confined before it, but it is implied. Okay. And then this, the last one, I call it a leaky confined aquifer. What that means is, like for example, here I erased these two arrows to indicate that no water can enter this aquifer from above or below. But suppose some water can enter into this aquifer from above or from below or both, then I will refer to the same aquifer. If some water is, let's say, some here the water is coming in from below or from above, then I will call this aquifer a leaky confined aquifer. Okay, so the same aquifer will be called confined if it does not permit any water to enter from above or below. But if it allows some water to enter from above or from below, then you will have what is called a leaky confined aquifer. Now, is it possible that any aquifer can be 100% confined? Maybe very, very unlikely that such an aquifer exists anywhere in the world, because some water may always leak from above or from below. So in reality, most aquifers are leaky confined aquifers. But if the amount of leakage is very small, okay, if due to geological circumstances, if the amount of leakage that's happening is really very small, then you can, for all practical purposes, say, although I know it is some amount of water is leaking, but for all practical purposes, you can think of it as a confined aquifer itself. Okay, so that's the distinction between the confined, the leaky confined, and of course, the first one that I spoke to you about is the unconfined aquifer. Okay, any questions before we go to the fourth category, the the perched aquifer? Any questions?
No, sir.
Okay, all right. Okay, so if there are no questions, we'll go on to the next category, which is the perched aquifer. Now, this perched aquifer is something that happens. This is an example of a. Actually, I'll draw the arrow a little bit closer. Okay, it's called a perched. Okay, now what happens here in this particular case is that I've drawn a small layer of some kind of fine grained soil. So whenever I draw a layer with these dashed lines, that indicates that it is basically relatively impermeable. Okay, that whenever I draw a unit which has got these dashed lines running through it, typically I'm trying to indicate that that dashed layer does not allow water to go through it very easily. So for some reason, let us say there is some clay present there. Okay, locally in that region alone, there's some clay present there. And when water infiltrates into the ground, it encounters this clay. So the clay is preventing the water from flowing away. So it just gets stored right above that clay and forms a local small aquifer over there. Okay. The rest of the locations around this clay layer, this little clay layer that you have, the water table is below that, right? So therefore, I create this due to this geological occurrence of a clay layer above the water table, which traps some water above it. Okay, this aquifer is called a perched aquifer. The word perched means something that is at a very at a height. Okay, now when we I mean, the whole thing is underground, so where is the question of it being perched? I mean, at a height. Well, it's coming from the idea that it is above the water table. So relative to the water table, the perched aquifer is above. So therefore, we call it a perched aquifer. Okay, now this the amount of water that the perched aquifer has might be relatively insignificant. Okay, but it might be sufficient. Suppose there is one family living here who has a house, and they need maybe, I don't know, 500 liters of water a day, and then in this particular region, if you get some continuous rainfall throughout the year, it's a lot of rainfall. So this perched aquifer keeps getting replenished by, although they keep using 500 liters of water every day, I keep getting more and more rain happening, and nobody else is drawing water from there. You are the only family there, and 500 liters is not a lot. You can probably this little perched aquifer may be able to supply water to you. Now this is also another of one of those reasons where you say my neighbor hit water at 20 feet, but for me I had to drill 50 feet or 100 feet, right? If the water table is at 50 feet and there happens to be a perched aquifer somewhere, and if you're lucky and you buy a plot and you build your house here, and your house is right here, and if you drill a well right there, then you'll find water at 10 feet or 15 feet. All your other neighbors have to drill 50 feet or 100 feet to get water, but because you happen to be near a perched aquifer, it's just a matter of luck. Okay, so that day, I think I didn't mention this, those guys who come around with the little spinning thing and say, I'll help you find water and all of that, that's all just fake. There's no magic way of finding out where there is water. Okay, it's impossible to predict where water will be, except to say that the most logical place to drill a well will be where the land surface elevation is the lowest. Okay, wherever your land surface elevation is lowest, that is the place where the water table might be closest to the land surface. So if you drill there, you might hit water at the closest depth possible, right? So it makes there is no other proven, scientifically proven method for finding water just by looking at a stick or rotating something or whatever, right? All of that is just uh, well, people have to make a living, so some people make a living by cheating others, so it's okay, it's not too bad. I mean, as long as you don't spend too much money on it, it's okay. Okay, they also have to survive. Let them survive. Okay, all right, so that's the distinction between these different types of aquifers. You have the unconfined aquifer, the confined, of course, which is a theoretical construct. No aquifer may be theoretically and perfectly 100% confined. There may always be some portion of water leaking in from above or from below. So all confined aquifers are in reality leaky confined aquifers. But if the extent of leakage is really small, then you may still classify it as a confined aquifer, and it's not too bad. And then the final category is the idea of the perched aquifer, and I've told you what are the circumstances under which such an aquifer might exist, or how it might be able to sustain water for a relatively small usage. Of course, some perched aquifers can be huge also. If I have a really big clay layer and it stores a lot of water, then it might be sufficient for maybe a community to live there, maybe some 10, 50, 20, 100 families to live there, and they may still be able to survive because by some fluke you have a really nice and big perched aquifer. But usually these perched aquifers are relatively small. They don't really supply a lot of water. Okay, now imagine if the same clay layer, if it was present here, if that same clay layer, where is my mouse pointer? Oh, there it is. Okay, suppose I have the same clay layer over here like this, and if this traps some water above it, that will not be called a perched aquifer because it is present below the water table, right? So it doesn't, it just adds to the water that's present in the unconfined aquifer. It doesn't, it will not be called a perched aquifer. Okay, for an aquifer to be called a perched aquifer, it has to be above the water table in the surrounding area. Okay, only then you will call that a perched aquifer. Okay, any questions?
Yes, sir.
Go ahead.
We can say that porous aquifer is the subcategory of unconfined aquifer, and
Yes,
leaky aquifer is the subcategory of confined aquifer.
absolutely. A perched aquifer, that's an excellent point. A perched aquifer is also an unconfined aquifer, right? Because there also the water table there, that local water table that's present there is at atmospheric pressure. Okay, thank you very much. That's a very interesting way of putting it. Perched aquifer is also an unconfined aquifer. Okay, and a leaky confined aquifer, as you said, is also a confined aquifer uh, with a little bit of leakage, right? So yeah, yeah. Thank you. That was an interesting insight. I never thought of a perched aquifer as an unconfined aquifer. Absolutely correct. Any other questions? Okay, so let's move on. Uh, okay,
Sir,
so
I have a doubt in the previous slide.
go ahead.
No doubt, but I want to clarify for myself.
Go
In
ahead.
aquifer, we can
Mhm.
say that permeability increases and porosity also increases. That's why permeability increases. So porosity increases, so the storage water also increases. If the same time the permeability increases, then the water transmissibility capacity also increases.
Okay, so you're saying, is there a relationship between porosity and hydraulic conductivity?
Yes, sir.
Yeah, so that's exactly where clay will fail the test. Clay has higher porosity than sand. Suppose I take a sand sample, right? The porosity of a sand sample may be 0.35 or zero point 0.4. Okay. And if I
Yes, sir.
take clay, it will have a porosity of maybe zero point 0.5 or 0.55. Its porosity is higher, but the
At the
permeability
same time, permeability also higher.
of what?
Sir, for aquifer, the porosity increases. At the same time, permeability also increases. That's why the capacity to draw the water from the water table increases.
Yeah. So okay. So if you can say those geologic units which have uh, a relatively high hydraulic conductivity and a relatively high storage porosity can be thought of as aquifer material, right? So it's that and that you said, that is the critical part, right? Both
Yes,
porosity
sir.
and hydraulic conductivity have to be high. Only then it will be characterized as a aquifer material. And as I said again, please remember that this classification or this distinction between these different materials is subject to the context. If you are in a place where there is only hard rock everywhere, even sandy clay will look like an aquifer because it's giving you some water. Hard rock will give you zero water, right? So that's why I think here that's why we were talking about this distinction. If you are in a place where there's only hard rock, even if there is sandy clay which gives very little water, okay, compared to hard rock, even sandy clay is better. So there, sandy clay will be called an aquifer material at that location in that context. Okay, but if you go to somewhere in UP Bihar, where which has got this nice beautiful sand gravel aquifer, right? Alluvial plain, Indo-Gangetic plain, beautiful aquifers. Okay, there a little bit of clay will slow down the water, and then there you don't like to see the clay, right? So there, the same sandy clay will not be called an aquifer; it will be called an aquitard or maybe even an aquiclude and so on, right? So the distinction is not really about, which is why I said you can't use a numerical value of say this much. If my hydraulic conductivity is this much, and if my storage coefficient is this, or porosity is this much, then it will be called an aquifer or it will be called an aqueduct. We don't do that. We call it, it's a qualitative classification. It is not a quantitative classification. Okay. We
Yes, sir.
cannot prescribe it for as a general rule for everywhere because it totally depends on the context. Okay. All right. Thank
Yes,
you.
sir.
Yeah, that's a helpful question. I hope others also benefited from this. Okay, so let's move on now. Now, when it comes to storage in aquifers, we have two different types of terminology that is used to refer to storage in the context of an unconfined aquifer and in the context of a confined aquifer. In the unconfined aquifer, we have a term that we call the specific yield, SY, which is the storage property of the unconfined aquifer. Okay. Now, the specific yield is basically uh, a portion of the porosity. So, my porosity N is nothing but the specific yield plus the specific retention. Now, these two words are kind of indicative of what is happening. Now, please remember, I'm talking about an aquifer. We are talking about a completely saturated soil sample, which means my entire porosity is filled with water. Okay. Now, just imagine this. Suppose I give you a sponge which is completely underwater. Okay. I take a sponge and put it underwater. Okay. And then I just pick it up from underwater. What happens to the water that is inside the sponge? As soon as I pick it up and I keep it on a dry table, okay, what will happen? Imagine
Water
this.
retention capacity is increases, like the field capacity of soil.
No. Wait. Just imagine this. Let's imagine that you're actually doing it. Okay. Imagine that I have a sponge that is completely saturated. It is underwater. I pick it up from inside. Okay. I just place it on the table. And now I want to understand what is happening to the water inside that sponge. What is going to happen to the water in that sponge? Is it going to remain inside the sponge?
No, due to gravity, it will go down.
Yes, sir. The remain water, I think.
Say that again.
Remain water in sponge.
Okay. So now the best way to do this is for you to do this experiment. Take a sponge, put it in water, take it out, and keep it on the table. You will start seeing some of the water that was inside the sponge will start to drain out. Okay. So what is the process that is making it drain out? It is the fact that whatever forces were holding the water inside the sponge are no longer able to hold it up, because once I take it out of the water, gravity is acting on that water molecules and it is getting drained out of the sponge. Okay. But let us say I keep it there and I wait for all the water to drain out of the sponge. Okay. After water will initially will drip out of the sponge very fast, and then it will slow down, and after maybe 5 minutes, 10 minutes, 20 minutes, whatever, the water will stop dripping. Then when I pick up the sponge, will it be completely dry, or will there still be water inside it?
Some water are there inside the sponge.
Some water will still be retained by the sponge, because now that water that is retained inside the sponge is being held back by the molecular forces of attraction between the sponge particles and the water molecules. Gravity is not able to pull it away from that molecular attraction forces, right? Those molecular forces are holding the water against gravity. Whatever water came out in the initial first 5 minutes or 10 minutes or whatever it is, that is the water that could not be held back because gravity was too strong. Okay. So that is exactly the analogy that I want you to use for this unconfined aquifer. I take an unconfined sample of a sample of soil from an unconfined aquifer. I take it out of the aquifer and I keep it on a table. Okay, some water will drain out of it, right? Over a few minutes, 10 minutes, half an hour, 1 hour, whatever it is. Okay, that water that drains out of the aquifer by gravity is called specific, is the specific yield. Okay, the water that still remains inside the soil sample after 1 hour or 30 minutes, whatever it is, after all the water is drained out by gravity, that water is a specific retention. Now these two, if you add them together, you should get the porosity, which is the total water that is held in that soil sample, right? So that's the way to think about this. We'll define specific yield in a more, now what I explained to you was a very physical demonstration of what specific yield is. Okay, but we have a more precise definition of specific yield. We'll come to that. Okay, but this definition is only applicable for an unconfined aquifer. Okay, when it comes to a confined aquifer, we use a slightly different terminology. It's called the specific storage, SS, or storativity, that is capital S. Sometimes it is also referred to as storage coefficient. Both these terms are used interchangeably. Storativity or storage coefficient, both of them use the symbol capital S. Or I have the other term, specific storage, which gives capital S with a subscript of again another S. Okay, so specific storage or storativity / storage coefficient, these are the terms that are used to refer to the storage property in a confined aquifer. Okay, so what is the relationship between the specific storage and storativity? So storativity S or storage coefficient S is simply the specific storage SS multiplied by the thickness of the aquifer. Okay, so these when I multiply the storage, specific storage by the thickness of the aquifer, I get the um, storativity or the storage coefficient of the confined aquifer. So the storage coefficient, like the specific yield, does not have any units, right? Porosity doesn't have any units. It's volume divided by volume, right? So it doesn't have units. So specific yield also doesn't have any units. Similarly, storage coefficient or storativity also does not have any units. Okay, but the specific storage has units of L minus 1, right? Because I multiplied by thickness of the aquifer, I get a dimensionless quantity. So therefore specific storage must have units of L minus 1. Okay, so these two terms are used to describe the storage in the different types of aquifer material. In an unconfined aquifer, we have specific yield, and in a confined aquifer, we have specific storage or storativity / storage coefficient. These terms are used in the context of these two types of aquifers. Okay, so now I think I'm out of time. Just let me just finish this off and then we'll stop. Okay, so specific yield, a more precise definition of specific yield is that it is the volume of water released by the unconfined aquifer per unit area per unit decline in head. Okay, so what is it? Specific yield is the volume of water released by the unconfined aquifer. So it's meter cube in the numerator per unit area per unit decline in head. So there is a meter cube in the numerator and a meter square multiplied by a meter in the denominator, right? Per unit area per unit decline. And this unit area that we're talking about is the plan area, right? So I've drawn this image over here. Let us say initially the water level was at this higher dotted line, right? I put a well here and I took out some water, right? The amount of water that I got for a unit decline in head. Unit decline could be 1 centimeter, 1 meter, 1 inch, whatever. Okay. Per unit area, cross-sectional area in plan view, whatever volume I got per unit area, per unit decline in head, that volume is referred to as the specific yield. So now the specific yield, this water that is released by the aquifer is released by gravity. It is drained from the aquifer, right? It's not extracted like by squeezing a sponge, not that. Just like we said, you take the sample and keep it out, whatever water drains out by gravity, that portion is the specific yield, and it typically ranges between around 5% to 25%, maybe 0.3. Okay, that's about the highest value that specific yield can take. Okay, so we will stop with that. And Friday is a holiday because of Independence Day, so we will not have a class on Friday. I'll probably record a lecture and send it out. and then we'll take it further from there. Okay. I should be back next week, so we will be meeting most likely in person. In case there is any change in plan, I'll let you know, and we'll continue to meet online. Okay. Most likely I should be back. Okay. Let's hope for the best. And thank you very much.
Sir,
Take care. Happy Independence Day. Yes, go ahead, Shantanu.
can we told that specific yield is in terms of discharge? How much discharge we even taken from a
No,
well?
when you say discharge, discharge has units of
Capacity
time.
of water.
No, it has the units of time, right? Discharge is flow per unit time. There's no time concept in specific yield.
Okay, sir.
Okay. Yeah. So uh, because when you wait for water to release by gravity, it takes its own time and it just gets released. So assuming that we have enough time to do this measurement, it's a time independent process. Okay. All
Yes,
right. So
sir.
thank you very much, everybody. If there are further questions, please email me. You can also post comments on the Google Classroom. Join the Google Classroom, those who haven't yet. Happy Independence Day, and see you all soon. Take care. Bye bye.
Thank you, sir. Looking forward to the offline classes.
Sure. Thanks a lot.